It says it's
Good.
recording. It says I can pause it, but I won't. So it must be recording.
All right, so BK, take it away.
Okay. So I need to be able to see you. Great. And then I need to share my screen. Yes, share. All right, can you see everything?
Can see it.
Yes. Yeah. Great. Okay, so this talk is entitled "How Do Mathematicians Believe?" It's it's sort of some of my ideas, some of the questions I find the most interesting in the world, and so I thought I'd start with something familiar to all of you. Goodness, come on, Zoom. Have you all seen this comic before from XKCD? I love XKCD, and you should definitely read it. Although most of what I'm going to do is disagree with this comic for this talk. So, what does it say? Sociologist on the left, and the psychologist says Soc is applied psych, which is applied bio, which is applied chem, which is applied physics. It's nice to be on top. And then the mathematician is way over on the other side, and she says, "Oh, hey, I didn't see you over there," right? And so the idea here is that mathematics is like the rest of the sciences, but is somehow extreme in some direction. They've used the word pure, which is a complicated word that we will come back to. Okay, so what am I really talking about here? I'm talking about a discipline. So it's a math talk. I might as well write a definition. So a discipline for me is going to be a web of ways of knowing, thinking, and engaging phenomena that are employed and evaluated relatively consistently by a community of people. And we'll talk about this a bunch. But why is this of interest to me? Well, my PhD is in mathematics, in tropical algebraic geometry, as we sort of talked about last week. But I do education research. And so I've moved between disciplines, and they're quite different in practice. Like, my experience with mathematics education is mostly as qualitative social science, which feels quite different than the way I was trained as a mathematician. And then within mathematics education, I am interested in the ways that students come to understand the discipline of mathematics, especially future teachers, what that means about their classroom and what yet another generation of students will think about the discipline of mathematics. So in addition to transferring across disciplines, I'm also interested in studying disciplines within my math ed research. So if I'm going to disagree with this comic, I should at least convince you that there's something worth talking about before we've spent a long time doing it. So here's some weird things I believe. I believe in stuff, but not things. I think evolution gave us quantity, consciousness gives us 2, and language gives us numbers, like, integers. I work with triangles, but I've never seen one. I sort of think we create definitions and proofs, but discover theorems. We'll come back, and I'll explain some of these at the end when we have some more context. And I accept the proof, the existence of true but unprovable theorems, which might be familiar, and something's going to come up there. So if you were, people have been there's this meme on the internet right now where people say like nobody, and then they say something about their discipline, and then people sort of run away. Like, this is not what people expect a mathematician to say, but I think these are consequences of being a mathematician, that I believe those kinds of things. And so this comic, what it's doing is suggesting that math is a science. And so let's sort of zoom in on the physicists. It sort of is math a science. I made the slides, so I get to choose that math is the light side and science is the dark side. But and I love science, and I have a degree in science. It's fine, but
rude.
Yes, I know. Scientists, the thing for scientists is that they're convinced by consistent data that matches models, and mathematicians approximately are not convinced by finite data. And just what do I mean by that kind of thing? What I'm really saying is that science is inductive, that generalize from examples and patterns, and mathematics is deductive. We derive conclusions using logic. And just as an example of how stubborn mathematicians can be, we have over 10 quadrillion examples that satisfy the Riemann hypothesis and no counterexamples. but we don't count that as justified. We don't count that as proven, as known for mathematics, although it's certainly close enough that it's useful to keep thinking about, well, what if it's true? Although that could also be seen as proof by contradiction strategies. And so I'm sort of contrasting math and science here. So let's think a little bit about how, what science is. So a classic book, although a little dated these days, is by Thomas Kuhn, The Structure of Scientific Revolutions. And Kuhn argues that being a member of a scientific community amounts to holding a paradigm, which is sort of a guiding collection, a collection of guiding assumptions that filter scientific inquiry. So it's partially ontology, like what kind of objects exist in the world, is partially epistemology, like how can we know things, and it's partially methodology, like how can we actually gather information. And the word paradigm does come from this book, or its popularization comes from the book in the 60s. You can see from the title that Kuhn is saying that that there's something sort of like political institutions here, and the book is about how there's different sort of phases, epochs, if you will, of science, and then something isn't quite working in their current model, and then there's a revolution. So he's using political institutions and their revolutions as a metaphor for science. And so my first interactive question for everybody is, Kuhn compares science to one other discipline other than political science and the physical sciences in this book. And if you haven't read it, I would like you to, those of you who are in the chat, maybe make some guesses in the chat. Other discipline Kuhn compares science to?
I read parts of that book a very long time ago. I have no memory of it. So
I don't want you to remember.
Yeah, exactly. So I think I'm qualified to answer this.
Religion.
Indeed. It's theology, right?
I have not read the book. I'm not.
Yeah. Round of applause for Nane. Yeah. He compares it to theology, the sort of what the world is and how we make meaning out of it. It is sort of the thing that he thinks is analogous. I've painted, of course, empirical data, and so some older work by Matt Ingalls and some more recent work by Christian Woods says that that absolutely is part of how we make sense of mathematical ideas. And certainly quantity and measurement are central to both disciplines. So it's not like we have no connection to each other, but at least in my framing, both disciplines are interested in theory. Science is interested in inducing to theory, and mathematics is interested in deducing from theory. And so certainly scientists would use mathematics to do that. They're going to build a theory. They want to understand the consequences of the theory they've built and to see if it's, does what they think it should do, or that it has logical coherence and those kinds of things. But for me, that doesn't mean that mathematics is a science. It just means that mathematics is useful for science. And so I think this is the thing that's sort of being captured by the comic, that the further along that spectrum of the sciences you go, the larger the weight of the deducing might be, or the sort of the abstraction level. Okay, so I've sort of argued that math and science are very different things, but that doesn't mean they don't share something in common. So maybe mathematics is descriptive like science. Maybe it's trying to describe something, but because it's trying to describe objects that are different than the physical objects that, say, physics is trying to describe, maybe that's why our discipline looks so different on the surface. So our second question, zooming in, descriptive like science, at least for many scientists. Well, we have some disagreement here, which already complicates the story. So in some sense, Platonism is answer yes to this, and formalism is answer no. I'm going to describe what I mean by these words, but it's going to take me a little prep to do. So we're going to have sort of three stand-ins for different perspectives on the nature of mathematics and mathematical knowledge: Goodall, Wittgenstein, and the Vienna Circle. And so Goodall's going to be a representative Platonist, and I'll explain that in a sec. But everybody one of our diagrams for these three groups is going to have a circle like this. Humans have access to the things inside the gray circle and do not have access to the things in the white space outside. That's how I'm organizing this. So for Goodall, humans have access to meaningful things, and the stuff that we don't have access to is meaningless. A subset of the meaningful things are the things that we can capture in language, and a genuinely proper subset for him. And for Goodall, this is stronger than some other people who sort of would equate the meaningful with the mathematical. So in some sense, what he's saying is that the real meaningful things are the universal, absolute, timeless thing. That's sort of the Platonism. And then only some of that can be captured in language. Only some of that is sort of can be articulated. But humans have access to more than that. And then the stuff that's outside that is meaningless. He would put empirical things outside there. So he sort of, there's a story of him stumping Noam Chomsky by saying to Noam that he was trying to disprove natural science. I don't understand what that phrase means. But he also sort of famously hated the idea of evolution because it seems to sort of fundamentally rely on randomness. And he would want things that could be deduced, things that were the way they are because they had to be that way. There was only one way they could be. And so he was really uncomfortable with those ideas. For the record, this chunk of the talk is mostly based on the brilliant book by Rebecca Goldstein, Incompleteness, The Proof and Paradox of Kurt Gödel. Highly recommend. Our second sort of player in this team is Wittgenstein. I'm going to call him the mystic, which you'll see why in a second. Again, humans have access to the stuff in the gray. He puts the meaningful outside and the meaningless on the inside, and he equates the meaningless with language. And so in some sense, so he's usually portrayed as this tortured Germanic genius, but I prefer to think of him as like a surfer. Yeah, man, if you can talk about it, then it's not real. Although he is quite intense. And so having recently rewatched Point Break, maybe we should think of him as Kurt Russell's character, like a surfer, but also very intense about it.
So I have a question. This Wittgenstein, is this, because there's Tractatus Wittgenstein, and then there's all of the other Wittgenstein, and they're completely different people. He just 180, right? So which one are you talking about?
I think this is the earlier one. So I was about to mention the Tractatus. So a subset for Wittgenstein of the language is mathematics, which he equates with sort of the trivial, and he's sort of saying here that that's things you can talk about, but that's stuff that carries no content. It's all tautological, and then of course he also equates the empirical with language, and that'll come up again later. There's some irony here sort of related to the question. One of his famous books, the Tractatus, is a book about how you can't talk about anything meaningful. It ends with this metaphor that if you've understood what the book was about, then it was a ladder that you've climbed up, that now that you've climbed up it, you have to sort of throw it away. And so it's that version of Wittgenstein here that is the contrast here. Mathematicians tend not to like Wittgenstein, in part because of this sort of mathematics equals trivial assumption. He was also really mean to Goodall. He's sort of the famous things that Goodall proved, Wittgenstein refused to read and said, well, that would be surprising, and mathematics can't be surprising because it's by definition tautological, and therefore I don't need to read it because it can't possibly be right. And so you can see why sometimes we're not the biggest fans. The third group here is I'm going to call them the Vienna circle, logical positivists. And again, humans in the inside. They believed humans had access to the meaningful and not the meaningless, and they wanted to equate meaningful with language. That's the positivism, that being cleanly articulated is the same thing as being meaningful to the positivists. And then they realized, well, we kind of need mathematics and logic in place in order to do a lot of that. So they sort of made that a subset of language, the trivial and the logical, and also mathematical for them. But what they were trying to do is establish what something empirical was. They were trying to understand what science could be. And in particular, they were a philosophy of science club dedicated to how there shouldn't be philosophy of science clubs. And as far as I can tell, no self-awareness that there was some irony involved in that. And this sort of connection where language and empirical were the same, approximately, they were trying to equate those. They really liked Wittgenstein. They didn't understand him because they disagreed with him, but they kind of worshipped him a little bit. And he came to one of their meetings and was so frustrated about them not understanding what he was saying that after a while, he just went over to the corner and started reciting mystic Vedic poetry at the wall, rather than having any more conversations with them. But they loved the idea that he was saying that something is, like, science is the same thing as, having a clear articulation of exactly how you would measure something. That doesn't mean you actually had to do it. Saying that a mountain on Europa is the biggest one on any moon is a claim that it would be hard for us to actually physically measure, but we could articulate exactly what it would take to measure it. So we have these three perspectives. They're different from each other, but they share some overlaps. So Goodall and Wittgenstein agree that there are meaningful things outside of what language can capture. Wittgenstein and the Vienna Circle agree that sort of science, the empirical, and language are the same, and that mathematics and logic are sort of a trivial subset of that. And Goodall and the Vienna Circle agree that humans have access to meaningful things and don't have access to meaningless things, but they move other elements around. So coming back to what do I mean by Platonism and formalism, we've already met Hilbert. He'll be our hero for Platonism, this idea that mathematics is descriptive and there's these sort of universal things that we're describing with the mathematics we find. Maybe our hero for formalism will be David Hilbert. All of the work that I've just described happened, well, they're all white guys in Europe in the early 1900s, and they're responding to a generalized sense in the area and time that cultural institutions had been failing, that sort of somehow something rotten had gotten inside and things needed changing. And so Hilbert proposed formalism, where mathematics was sort of only internally referenced. It didn't reference anything outside itself to sort of fix that issue. And so that idea, Nazism and Zionism and this idea of purifying our knowledge all arose in sort of a similar context. And well, if anyone tells you that history has nothing to do with mathematics and mathematics has nothing to do with history, then you can give them this example to say otherwise. But what would the mathematics look like in Hilbert's vision? So let's do a little mathematics. This one comes from Hofstadter's The Gödel Escher Bach, the Eternal Golden Braid. So I'm going to ask you a question in the middle, and if you've seen it before, don't play along. But if you haven't, I'll warn you before we give away the answer in case you want to like turn off your sound for three minutes or something. So a formal system has three kinds of things. It has an alphabet. So in this particular one, what are the sort of objects in here? They're finite strings made out of the symbols M, I, and U. Any finite string of those is sort of the objects that this formal system is talking about. The second ingredient is rules of inference, how you can conclude something based on something else. And we're going to have 4 rules of inference. We'll look in more detail at these 4 so you don't feel like you have to memorize them. But just to be clear, X and Y are finite strings and they can be empty. So there's just saying, this first rule just sort of says, if you have a string that ends in I, that's a theorem that's true, then you can conclude that that same string where you append an M is also true. It's also a theorem. And then the third element is you sort of need some starting places. I think of it as the box of truth. And we're gonna make one assumption. We're gonna call it, think of it like it's our axiom. We're gonna assume MI is a theorem. Okay, so what can I do with this? Well, MI is a theorem, and that's of this form. It starts with M and then it has some string, and that's a theorem, and therefore I can use the second rule to conclude that M, where then I have 2 copies of the rest of the string, is also a theorem. So if I use rule 2, I can take MI and as a theorem and conclude that MII is also a theorem and hence also belongs in my box of truth. I could repeat that and get MIIII, or I could go back to the MII and use rule 1, which says if you have a string that ends in I, you can append an M to it, and it's still true. That's rule 1. And then if I look down here at my M with 4 I's, I can use rule 3. Rule 3 says if I have a string that starts with an M and then has 3 I's adjacent to each other, I can replace those 3 I's with a U, and I get to choose because X and Y could be empty. I can choose whichever one to be I and the other one to be empty, and so I choose the last 3 I's, and so by rule 3, I have concluded that MIU is a theorem. And so the question, I mean, in general, what mathematicians do is we say like, oh, I wonder if this thing is true, right? And so is MU a theorem? So I'm going to give you maybe 2 minutes. You can use the chat. Again, if you've seen this one before, don't ruin it for people. And featured friends, if anybody would like to share their thinking either as they go or as they've done some. Nice. Does anybody have any thoughts they'd like to share? Adriana, what are you thinking?
Sorry. All I was thinking was that I saw you give this talk and I knew what this was supposed to be.
That's right.
I got kind of stuck there, but
okay, that's fine. I've forgotten you've seen this. That's right. Yeah. All right. Well, we need at least one other person to share before we move on. Somebody who hasn't seen it before. The chat is blowing up.
Yeah.
But I can't see what people are saying.
Spencer says, okay.
Yeah, so somebody thought, well, if we had MIII, then we could get mu. But we haven't seen that yet. They realized that it was M quadruple I is what we saw.
Great. Okay, great. I think that's a good place to start. So this is the part where if you want to keep thinking about this on your own, plug your ears for a minute or two. The observation there is if you had 3 I's only, you could do it, and that would be great. And so rather than remembering, and so the number of I's really matters, and rather than remembering the exact number of I's, I'm just going to remember the number of I's mod 3, or I'm going to remember the remainder of the number of I's when we divide by 3. And so there's 3 possibilities. There's remainder 0, remainder 1, or remainder 2. And then I'm going to see what the rules of inference would allow us to do from each of those. So if we look at rule 1, and we have, let's say we have remainder 0 I's, i.e. we have 3 Ki's, and we use rule 1, what's our remainder after using rule 1?
Rule 1 doesn't change the number of I's.
Right, so it doesn't change the number of I's. And so if we had remainder 0, we still have remainder 0 after adding an M to the end of it. Similarly, if you look at rule 4, it deletes 2 adjacent U's. That does not change the number of I's. Rule 3 does change the number of I's, but Amy, do you agree that that won't change the remainder?
Yeah, it doesn't change the number of I's mod 3, so
right.
Yeah.
And then nothing in this chunk has anything to do with the fact that we were remainder 0. That's true at all 3 places. Those rules keep the remainder the same. Now, rule 2 might do something interesting. So if we have remainder 0 and we use rule 2, so we had 3 K I's and we use rule 2, how many I's are we going to have? Well, really, what's the remainder?
Still 0.
Yeah, if you have 3K, you double it, you get 6K. That's still divisible. Sorry, I couldn't see who was the person about to talk. Okay. So rule 2 also doesn't do anything for remainder 0. But what if we have remainder 1? What does rule 2 do? Well, 3K plus 1, you double it, get 6K plus 2, which has remainder 2 on 3. And 3K plus 2, when you double it, you get 6K plus 4, which is 6K plus 3, which is divisible by 3, plus 1. So you end up with remainder 1. So is MU a theorem?
Not based on this information.
So video, how many of you think MU is a theorem? Thumbs up. How many of you think MU is a theorem? Thumbs down. I can't see very
You can
many.
also tap yes and no in the
Yes, you can.
participant list.
All right, okay, but I actually did something sneaky. So definitely looks like no, correct? But the problem is what we proved, and that's because this basically a proof is a walk along this directed graph, and we need it to start at remainder 1 from here and end at remainder 0 to be here, and there is no path in this directed graph that would do that. But what we actually proved is that MU is not provable. Not that MU is not true. Right? And not only did we do that, we sort of stepped out of this formal system and made number theory and graph theory talk about this system. So like the number theory and the graph theory were not inherent in the system; they were sort of meta commentary about it, and that's the brilliance of some of Goodall's upcoming work. So what Hilbert wanted, so he sort of famously said that if you can't replace point and line with stein of beer and table, then you're not being careful enough with your geometry, you're bringing in your intuition. And what he was trying to do is he was trying to remove this sort of external influences on mathematics. And this distinction between true and provable becomes a problem for the formalists, right? What Hilbert wanted, and a lot of his sort of Millennium Prize type goals for the mathematics community, was these sort of new challenges, philosophical challenges to mathematics that became salient if you took formalism as the stance that mathematics took in the world. And Goodall actually contributed positively to that. He proved that some versions of logic have the desired properties that Hilbert wanted, but the proofs were much harder than you would have expected from something that ought to be sort of, from Hilbert's perspective, tautologically true about mathematics. And so that should have been worrisome. And then Goodall did something else. So Hilbert proved that if you could do this, if you could prove that arithmetic was complete and consistent, i.e. that everything that was true was provable, and that no statement was false and true at the same time, then Hilbert proved that you could use that to prove that geometry was consistent and complete. And so he sort of said, like, I can build, if we can get it started, I can build on top of that. That was his plan for cleansing knowledge, but Goodall proved otherwise. So Goodall's incompleteness theorem says, approximately, I'm waving my hands here, in any formal system rich enough to include arithmetic, there are statements that are both true and unprovable. And so that his key idea, in addition to that sort of meta commentary, was something like this. So this very sentence is unprovable. So let's step back first and say, like, well, this very sentence is false. If that sentence were true, then its contents would be correct, in which case it would be false. So if it's true, it's false. And if it's false, then its contents would be incorrect, which would be that it's false. And so if it's true, it's false, and if it's false, it's true. And that's a problem in a consistent system. So if we assume that the system Goodall is working in is consistent, that a statement can't be true and false, well, this very sentence is unprovable. If it's false, then what it says is incorrect, in which case it would be provable, and provable things are true. So if it's false, it's true. So it can't be false. Therefore, it had to be true, assuming that the system was consistent. It has to be true, and therefore its content is correct, which is that it's unprovable. So Goodall's clever idea is that just like we did in our previous example, in Hofstadter's example, he made number theory talk about itself in a meta way with the sentence, this very sentence is unprovable. And there's a really cool diagonalization or diagonal theorem lemma going on there that's really super fun and beautiful and multi-layered and other kinds of things. And as a corollary, you can't prove, Hilbert's dream was dead. You can't prove a formal system is consistent and complete from within, because a proof of that would then imply that anything that is true, true must be provable, and then that would contradict Goodall's previous statement. And so this shows that you could never have the thing that Hilbert wanted. You can never make arithmetic the sort of perfect version that doesn't reference anything outside itself, but everything that's knowable is provable. And Hilbert, unlike Wittgenstein, had the grace to admit that his dream was dead, but after reading Goodall's work. But being descriptive, so coming back to the bigger question, being descriptive fixes this issue. So if I tell you I taught high school in New York City last year and that I needed to find an apartment that I could afford on a teacher's salary that let me have my cats, that had good light so I wouldn't go bonkers during the year, and that let me get to work with a reasonable commute, you might start to worry that that's not going to be possible. But if I told you I found an apartment that let me keep my cats, that I could afford on my salary, that had good light and that had a good commute, you're no longer worried about those things being internally inconsistent, because there's an actual model of an object to which they're applying. So Goodall used this to sort of claim evidence that the human mind had direct access to truth, and people like Roger Penrose use it to sort of argue that computers and brains are different. My reading of these arguments is circular. It is that they're circular, that they sort of declare, well, they're different and therefore they're different. But these ideas inspired other things like Turing as well. Okay, so at first we asked, are math and science the same? Well, we use different disciplinary tools. And then we said, well, is it descriptive? We got sort of a yes and no question. But along the way, I kind of implicitly assumed mathematics was this thing outside of the people, and that we were sort of engaging in some way. And maybe this discussion has been driven by me making that assumption. Maybe I shouldn't have made that assumption. So let's look inside the humans. This one's the biologist, so let's look inside them biologically. And there's sort of two very different ways of looking at sort of what humans do with mathematics. I'm going to loosely call them syntactic and semantic. Syntactic will sort of be the closer to the structural, formal, and semantic will be the sort of more descriptive, meaning-based one. And so I'm just going to talk a little about both of those in context. This quote from Valéry says, mathematics is the science of actions without objects, and for that of objects we can define through action. Sort of saying that it is descriptive in the same kind of way. We're just describing slightly more abstract objects. So one of my favorite papers of all time is Anna Svard's on the dual nature of conceptions, and she helps us think about what these mathematical conceptions are inside the brain. And so she has this process. So let's think about counting. So for very small children, doing counting is this like weird dance that adults keep asking them to participate in. And it's sort of this, it's this external thing, and then it gets interiorized. And eventually it gets condensed into, like, you can imagine counting, and the child in particular could imagine counting without having to actually have objects to be counting, right? So counting becomes a process that can sort of be thought of a little bit more generally without having to talk about doing it in a particular context. And then that process starts to turn into an object, reification, from the Latin roots res facio, which means thing make. So if you don't like reification, you maybe replace it with thingify or objectify. And so the counting eventually starts to become a count, right? The result of it becomes an object. The result of the process becomes an object. And we can, I think the word is de-thematize these. We can think of the process and the object at the same time, but starting to think of it as an object is a key move. And Svard points out how at the same time that it becomes an object, it becomes an object on which new kinds of processes can start acting. So maybe the counting on strategy there, or if you like, arithmetic, building on that, and then that keeps spiraling upwards, and maybe on top of arithmetic you build algebra, and on top of algebra you build abstract algebra. It's not nearly so clean as all of that, but the sort of idea that processes can become objects is sort of the core of her idea there. And a number of years ago at the Research on Undergraduate Mathematics Education ROOM conference, I saw a talk that collected some neuroscience data about this, and they observed that when learning a new process, activation was in the sort of frontal part of the neocortex, where associated with conscious control and decision making of a process, but eventually the activation would move to a place associated with things more like imagining a 3D object. And so at least, I mean, it was a small amount of data a long time ago in one particular context, but this is suggesting that, at least in terms of electrical activity and connectivity of the brain, that there was some evidence that that by engaging in processes, our brain started to produce, from its perspective, new objects. And so that in that sense, the brain is describing a thing, even if it is a sort of descriptive thing inside itself. In contrast, and this is where my heart lies most of the time, there's sort of syntactic, although this slide is thinner. Eckhart says, I shall here present the view that numbers, even whole numbers, are words, parts of speech, and that mathematics is their grammar. But this sort of syntactic perspective has some philosophical questions for me, like where does logic come from? I don't know how inside a logical system I can answer this. I mean, I know some philosophers are thinking about different kinds of logic, and I'm not saying I don't value that work. I think it's really lovely, but is there something about the world, is there something about our brains that sort of only allows certain kind of logic, or is there something more universal that said logic had to be this way? And certainly we don't talk about logic very much, other than sort of assuming it works the way we want it to when we're doing mathematics. A number of years ago, I watched a brilliant talk by Anirudh Patel, who's a neuroscientist who studies music. And he was presenting evidence that the same part of the brain processes grammar and harmony, musical harmony and grammar, in the sense of that there might be mental machinery that processes abstract structures, and both of these are discrete combinatorial systems. My personal belief is that mathematics is also powered, so not a metaphor, that is literally powered by the same thing. Although I engage mathematics very much through the words, as you might have noticed. And just a last quote to connect the music and math. Sylvester says, "Mathematics is the music of reason," which I think is a beautiful quote, if a little vague. So what we saw here is that my question before, like, is mathematics descriptive or not? Well, there's evidence of yes and no. And at least when it gets to electrical activity inside the brain. And so maybe we're asking the wrong question, or we're asking it of the wrong part of the system. So in that sort of chunk, I talked a little sort of maybe more biologically about the people, about the brain. I could have talked about the mind, and I don't mean to claim that there are different phenomena for each other, but they're definitely different foci. We're going to sort of focus on something slightly differently. So one of my favorite perspectives here is from William Perry on the epistemological development of college students. And he observed 4 stances towards knowledge that these college students took. Dualism, where knowledge was sort of right and wrong and absolute, and the student's role was to find a good authority and figure out what the authority thought. Multiplicity, where knowledge came from individual perspectives, and students needed to be spending the time thinking about what they believed. Relativism, which isn't used the way it is used in other contexts. Here, relativism means knowledge comes from arguments and evidence. And then, although his research support for the final chunk is thinner, relativism with commitment, where I suspect you've all known an obnoxious middle schooler who would argue for anything without regard to whether or not they believed the starting point of that. And so sort of relativism commitment was starting to think about the foundations of the arguments in a stable way for the individual. Perry, there have been a number of follow-ups to Perry's research, very important. The most important one in my mind is women's ways of knowing. Perry was doing his work at Harvard in the 1950s, an extremely privileged group of mostly white men. And so there are a couple of things he didn't see and a couple of things he didn't understand. And so one of them was in women's ways of knowing, they have a much more diverse group of women, and they noticed that Perry missed that some people don't feel like they're allowed access to knowledge at all, so they can feel silenced. And well, I'll come back to a couple of the other things, but Perry did notice some changes in the positions he was seeing in the college students. And those have been attributed to things like the Korean War and the Vietnam War, where people were coming to college sort of believing different things about whether or not institutions should be trusted and whether or not they were working and whether or not they were doing what they ought to be doing. And so the question is, do we see something similar in mathematics? We do. So there's a famous paper by Harrell and Sauter called Proof Schemes, which asks what kinds of things convince students about mathematical statements. And they found 3 types of proof schemes. Authoritarian, which sort of meant like, well, that's what the algorithm said, or the computer said, or that's what my teacher told me. Empirical, we've done a couple of examples, and so it seems to generalize. And analytic, which is that knowledge is the result of arguments, and that matches really well with sort of dualism, multiplicity, and relativism. Within analytic, there's sort of the formal and axiomatic, whether or not the axioms are truths or just assumptions in there. And so we're seeing the same thing. We're trying to do the same thing in general as the sort of the goal of a college education. What would this look like inside mathematics? Those of you who've seen me talk might have seen these 2 examples. I'm going to show you a pair of concept maps from the same student on the first and last day of a modern geometry course. I'm going to look in a little bit of detail here. So she says, mathematical truth introduces undefined terms, definitions, and examples, which provide intuitions, decidability, and logic, which is needed for construction. It's needed to test, which articulates contradiction, and it's needed for evaluation, showing consistency, which creates deduction, and the consistency also produces theorems, corollaries, lemmas, and axioms. I'm going to pause here to let the chat notice. I'm curious what you notice. What pops out about this concept map about mathematical truth from the students? And then friends.
Chat might be too busy memeing about sandwiches to analyze this.
I started saying up chat, and I'm like, oh god.
Sorry, I apologize.
It had to happen. So the thing that I'm noticing about this diagram is two things that I noticed, and one of them is it feels backwards to me, and the other one is that it also feels like a set of instructions for how to do geometry problems, like that's the order that it's in. It's like, if I'm going to solve a problem in this class, this is the order that I do things in. You know what I mean?
Yes. So there's the flow, and the knowledge flows from truth, mathematical truth, towards these other things. Good. Anybody else notice anything?
One thing I noticed is that there's a process, or like a verb, like introduces, producing, and then it leads to something, which kind of reminded me of kind of like the reification piece, that there's like a thing that gets created from a process.
Mm-hmm. Mm-hmm.
It's almost like Bloom's taxonomy.
Mm-hmm. Good.
It's interesting that there's no like wrapping back, right? Like the arrows all go forward and nothing else, you know, the only place where you have sort of 2 things connected, they're in the same box of like theorems and corollaries, right? Like nothing's going back. So it starts with truth, and then there's this whole thing around, and well, it's just interesting that nothing like goes back, right? Like, you know, like what happens if you get a contradiction? Does that, like, what does that mean? Like, I don't know. There's some, it feels too clean from like everything.
Can I say another one?
Yeah.
Is that axioms, lemmas, and theorems and corollaries, they're all like on the same footing there.
Uh-huh.
Yeah.
So the students noticed a lot of the same structural patterns you did. And one of the things I did after they did their post-course map is I gave them back their original and asked them to reflect on the changes. And many of them were much more cyclic and things like that. But the one that, so when I've given these to mathematicians to evaluate and give them more than 30 seconds, the fact that axioms, lemmas, corollaries, and theorems are all sisters of each other really pops out to mathematicians, that axioms are different than that. And in lots of the other maps, definitions do a similar kind of thing. And that...
Okay. Did you give them these words? Like, did you say, okay, make sure your map says axiom, or was the idea of an axiom student produced?
I gave them about 15 words they needed to include. I put those words on little pieces of paper so that actually move them around before writing their draft. They were required to add at least 2 extra words of their own. Yeah, so I gave them some of the ones that needed to be there, but they added to them.
BK, how old were these students?
Juniors or seniors. Well, okay. So these students had taken an intro to proof discrete math class, a proof-based linear algebra class, a proof-based abstract algebra class, a proof-based real analysis class, and they were in my proof-based modern geometry class. And so on the one hand, it's a little worrisome to some of us as educators that this map essentially doesn't make sense to an expert perspective, and this role, the fact that axioms and definitions behave unlike we'd want them. From a student perspective, it is totally reasonable. As Amy pointed out, this is sort of this is sort of the process of doing a lot of the problems, and for them, it's kind of irrelevant whether something's an axiom, a theorem, or a definition. It's a statement that's in the book that they're allowed to use. So this helped me make sense of that behavior in students that I hadn't really understood beforehand. But in contrast, let's look at the same student's map at the end. She says, mathematical truth. First, we have ideas. From these, we assume, yay, definitions, intuitions, and axioms. And through logic, rigor, and persistence, we can use constructions and examples to make conjectures. Then we can apply a type of evaluation where my cats fight with each other. Kittens. Where we use deduction, contradiction, and decidability, only to find out that we still have undefined terms. So for her, undefined terms was a negative. I meant undefined terms in the Hilbert sense, where it was positive that we could use this word consistently and didn't have to define it. It meant we weren't using our intuition. So I revised the course subsequently to make sure that that idea about what mathematics got in the course more cleanly. But from undefined terms, she says, so we test yet again and look for consistency in our results. And if we have it, then we have found theorems, corollaries, and lemmas, the ones that experts want to be sisters. And then we have proof that there is such a thing as mathematical truth. Yay. So this one is more cyclic. It sort of flows from and to. The process is definitely about constructing knowledge in a more nuanced and subtle way. And mathematicians look at this and are often like, yes, I understand what these connections were. They often look at the first one and say, I have no idea what any of those connections were attempting to capture. And so, at least in terms of the course, that's evidence that us thinking about the philosophy of math in the context of triangles, it had an impact for this student. And I've written a little about this in other contexts. So just to triangulate this with something else, this is a paragraph, well, sort of a lately edited paragraph from the textbook that the students wrote together, geometry textbook in the form of a wiki. The majority, I've added the emphasis to highlight the epistemological words. So the majority of what we hold to be true in any given mathematical system comes from a proof, generally called a theorem. But there is so much more to a system than that, as you will soon learn. This is the foreword to their textbook. The axioms, or basic assumptions within the system, are universally known propositions that are used without proof. An axiom is a premise or starting point of reasoning. We can think of an axiom as being so evident that it is accepted as true without controversy. An axiom is a proposition that is not and cannot be proven within the system that is based on them. We get these intuitions from a priori knowledge or experiential belief. That is really all mathematical truth is, the deductions we reach from objects we already know or assume to be true. And that know or assume, my students really wanted to Kant's synthetic a priori truths. They wanted axioms to be true, and therefore geometry knowledge theorems to be true. And a few of them were more like me that believed that the truth of those things is relative to your axiom system. And so I think we could spend, we're running short on time, but we could spend some time thinking about this as evidence for relativism and relativism commitment inside this framework here, or evidence that they've acknowledged the existence of the analytic framework in terms of the proof scheme. But the reason I came back to this slide is to point out that I think the goal of a liberal arts education is to help people realize that different questions require different disciplinary approaches and different sort of accepted truths that you're willing to start from. And that the education is about building those methods up and contrasting those methods. And Dave Kung has pointed out that in the same way that Perry noticed that students took different stances, and if they were more used to pushing back against the government and the Vietnam War, Dave pointed out in his TED Talk that some of the things we do in mathematics aligns with an authoritarian perspective, and that we're doing these kinds of things implicitly, even if we're not always noticing that that's what we're doing or bringing them to the surface. And so again, I asked, this is clear evidence that thinking about mathematics in the context of the people who are doing it is really important. And so that's sort of thinking about the mind, but implicit in all of this is that there's a group of people going on. And so my sociology one is kind of short, but here's a perspective. It's called the Emergent Perspective. The original version is due to Cobb and Yekel. I believe this image is from Rasmussen and others, and has been updated. It has a sociological and a psychological half on each side, and they're assumed to be reciprocally related, that the sociological and psychological elements are two sides of the same coin. So classroom norm might be that only one person talks at a time, and that might correspond to beliefs about responsibility or beliefs about how learning work or beliefs about conversation. And then there could be some things that are more specific to mathematics, like what counts as an elegant argument, or which warrants have been so thoroughly vetted that we don't have to say them out loud. They're truths that we in this community accept to be true. And that corresponds to sort of the beliefs about those same kinds of things. So one reading of what I've been doing in this talk is arguing that rather than math is very, very, quote, pure versions of the other things, you could read what I've done as arguing that math is applied sociology, psychology, and biology. But we haven't really talked that much about what mathematics is. We've mostly been sort of talking about what it's not. So let's think a little about that. First, a quote from Hardy: "A mathematician, like a painter or poet, is a maker of patterns. If his patterns are more permanent than theirs, it's because they're made with ideas." I don't like the sexism. I do like the idea of mathematics as poetry, and as this sort of like attempt at timeless poetry, although the timelessness is complicated. The next one is from Deepak Chopra, who sometimes says profound things and sometimes says silly things. I think this one's profound. Mathematics expresses values that reflect the cosmos, including orderliness, balance, harmony, logic, and abstract beauty, which I think is sort of a lovely idea. But let's return to those weird things that I thought. I believe in stuff, but not things. What I mean by this is I accept that the physical world exists. And that's what stuff is. But things, when we take that stuff and we think of that stuff as objects, I don't think that exists in the world. That thinking of it as an object is something that happens inside the mind. And so inside the mind, those I believe in them, but that's not a physical thing. Similarly, I work with triangles, but I've never seen one because triangles are made out of lines that are not made out of stuff. And I had a colleague, well, I sort of replaced him in a previous institution, had a small stroke. He was fine, but before he retired, and he lost the ability to look at line segments and tell if they were approximately parallel. And while that's not quite proof that parallel as a thing that happens in our minds. That's sort of like abstraction from the physical world to the world where something infinitely long and made of nothing could have properties. That happens in the mind. What I actually think about mathematical truth for this one is I think of mathematical truth like dream truth. Like something can be true in a dream, and like you could just know it's true, and that the dream can be consistent, and there could be consequences of that thing being true, but that doesn't mean that truth is sort of universal to the world, but it's true within that system. So what is mathematics? We're almost there. If you ask me what tools I use, I think I look like a philosopher. Deductive reasoning. I don't think that'll surprise anyone after the last hour. If you ask me why I study mathematics, I think I come out like an artist or musician. I think the ability to abstract in this way is a representation of our humanity, and I think everyone should have access to it. I love that math is useful too, and I love that people do useful things with math, but I think everyone should have access to it because it's an expression of our humanity. And if you ask me what I study, I think I look like a linguist because I care deeply about the words. In particular, depending on which perspective you take, our objects are our definitions, in contrast to the scientists whose definitions are trying to describe something outside themselves, and therefore we operate with them in a different way. A number of years ago, which I'm realizing is a decade ago, my students took this stance on me and said that I should, on my business cards, it should say word ninja rather than mathematician. And so if you were wondering where my Twitter handle comes from, it comes from this group of students a decade ago saying that that's what they thought a mathematician was. But so since I was talking about words, what does math mean etymologically? It comes from the Greek mathematikos, which loosely means inclined to learn, which I think is pretty badass, that our discipline basically means like universal learners, which I think is really cool. But I said we would return, and I'm glad we have 2 minutes to do it at the end, to this word pure. So Rochelle Gutierrez has argued, successfully in my opinion, that mathematics operates as whiteness, that it structures spaces, that in particular, the thing that this talk was about was how our disciplinary worldview is something we often don't talk about. And that making itself default and invisible gives it tremendous power in the same way that whiteness functions. And Sarah Hattinger has argued, not only metaphorically, but mathematics is central to the construction of the Western rational objective individual, and therefore is a necessary element in white supremacy. And so what am I really interested in here? I've been talking about a discipline. So this definition is going to make a lot more sense than it did an hour ago. A discipline is a web of ways of knowing, thinking, and engaging phenomena employed and evaluated relatively consistently by a community of people. I'm interested in this in particular for my students who are future teachers. They are going to go represent this discipline out in the world. And I believe that if they can't acknowledge that mathematics has a disciplinary worldview, if they can't question the defaultness of some of the worldviews we have about mathematics, then that limits their ability to share mathematics in a way that is humane with their students. And I taught high school full-time last year, and it took, I have a PhD and 15 years of experience, and I'm very confident. And it took everything I had, to sort of use Gutierrez's word, political conocimiento, to resist structural and administrative pressures for me to do terrible things in the name of mathematics based on other people's math phobia. And so it's really important to me that my future teachers can not only think about mathematics in productive ways, that they can critique those systems that might be having the opposite desired impact on students. And so I think that is the end. Thank you so much.
Everybody join me in thanking Brian. So we've hit our hour, but if you need to check out, now's a good time. And if you want to hang around and ask a question or two, I think we have a minute for that.
Yes, I can stay.